Have you ever wondered why the universe is so perfect? Why everything seems to fall into place just right to allow life as we know it? Well, you're not alone. This idea that the universe is somehow perfect has captivated thinkers for centuries. From the ancient Greeks who marveled at the harmony of the celestial spheres to the Renaissance scholars who saw divine geometry in the cosmos, the perception of a perfect universe is deeply embedded in our history. And it's not just about aesthetics or philosophy. It's about the very mathematical and physical constants that govern our universe. From the smallest subatomic particle to the vast cosmic structures that span billions of light years, there's an intricate balance in play. A delicate dance of forces and constants that, if altered even slightly, could have resulted in a universe where life, as we know it, could not exist. This is the concept of fine-tuning. It's the idea that the fundamental constants of the universe are set just right to allow the formation of complex structures from atoms to stars, galaxies, and even life itself. It's about the Goldilocks principle, where everything is not too hot, not too cold, but just right. But what does this all mean? Are we just incredibly lucky? Is there some cosmic designer who set the universe up just for us? Or are there perhaps countless other universes out there, each with its own unique set of constants? And we just happen to live in the one where conditions are right for life. In the journey of understanding this perfection, we will encounter the idea of fine-tuning. It's a concept that will take us from the smallest scales of quantum mechanics to the largest scales of the cosmos. It's a journey that will challenge our understanding of the universe and our place within it. Picture a finely tuned machine, each part playing its role perfectly. This, in essence, is the universe. The universe operates on a delicate balance, a fine tuning of physical constants. Without this precise tuning, life as we know it wouldn't exist. What are these constants? They are values embedded into the fabric of the universe, like the speed of light or the force of gravity. These constants are incredibly finely tuned. For instance, if the force of gravity was even slightly stronger, stars would burn out too quickly for life to develop. If it was weaker, stars wouldn't form at all. Similarly, the strength of the nuclear force holds atoms together. If it were any stronger or weaker, we wouldn't have the diverse array of chemical elements necessary for life. It's as if the universe has been engineered for life. The universe seems to be fine-tuned for life, but could there be a reason for this? Enter the anthropic principle. This principle asserts that certain properties of the universe appear as they do because if they were any different, we wouldn't be here to observe them. It's a bit like saying, the universe is perfect for us because if it weren't, we wouldn't exist to call it perfect. This isn't to say that the universe was designed for us, rather, it flips the question. Instead of asking why the universe is perfect, it asks why we perceive the universe as perfect. The answer, because we exist. We exist because the universe has properties suitable for life. So, the universe's perfection might not be so coincidental after all. Let's delve into the specifics of these cosmic constants. These are fundamental values that shape the universe as we know it. They are the bedrock of our physical laws, and they're remarkably fine-tuned, allowing the universe to exist in a way that can sustain life. One of these constants is the speed of light, a staggering 671 million miles per hour. It's the cosmic speed limit, and it influences everything from the propagation of electromagnetic waves to the laws of energy and matter. If it were even slightly different, the universe would be unrecognizable. Consider the gravitational constant too, a number that determines the strength of gravity's pull between two bodies. Its value is incredibly sensitive. If it were a fraction stronger, stars would burn out too quickly for life to evolve. If it were a fraction weaker, stars might not form at all. Then there's Planck's constant, the cornerstone of quantum mechanics. It sets the scale for the strange, counterintuitive world of the very small, where particles can be in two places at once and cats can be both alive and dead. Without this constant, the weird and wonderful world of the quantum would cease to exist. And let's not forget the cosmological constant, a value that describes the energy density of the vacuum of space. It's responsible for the accelerated expansion of the universe. If it were any larger, galaxies, stars, and even atoms might not have had the chance to form. There's also the fine structure constant, a mysterious number that governs the strength of electromagnetic interactions. It's critical for the formation of atoms and the existence of chemistry, biology, and life as we know it. These constants play a vital role in the universe's grand design. They're not just numbers. They're the ingredients that make the universe a place where stars can shine, planets can form, and life can emerge. They're the reason why the universe is not just a chaotic mess, but a beautifully ordered and intricately balanced cosmic ballet. Stars, the building blocks of galaxies, but how are they formed? Well, the very existence of stars and the elements they create hinges on the precise tuning of physical constants. Picture a cosmic recipe. Start with a cloud of hydrogen and helium, the lightest and most abundant elements in the universe. Under the pull of gravity, these atoms begin to coalesce, forming a dense core. As the core's density increases, so does its temperature, until it's hot enough to ignite nuclear fusion. This is the pivotal moment when a star is born. Nuclear fusion is the heart of a star, where hydrogen atoms are squeezed together under tremendous pressure to form helium, releasing energy in the process. This energy not only lights up the star, but also creates heavier elements like carbon and oxygen, the very elements necessary for life as we know it. Stars are the cosmic forges where elements necessary for life are created. From the vast cosmic stage, we zoom into the formation of habitable planets. This process is a delicate dance of cosmic conditions. The first factor is the star around which the planet orbits. It must be stable and long-lasting, providing the right amount of heat and light for a significant period. Then comes the planet's position, sitting comfortably in the Goldilocks zone. This is the distance from a star where it's not too hot, not too cold, but just right for liquid water to exist on the surface. The planet's size matters too. It must be large enough to hold an atmosphere, yet not so large that its gravity prevents life from thriving. And let's not forget the planet's composition. It must contain the right elements for life, like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. In this perfect universe, even the right conditions for life seem to be in place. Gravity, the invisible hand that shapes the universe. This fundamental force is the master sculptor, carving out the vast cosmic structures we see around us. It's the silent director, setting celestial bodies in their eternal dance across the cosmic stage. It's gravity that pulls together clouds of gas and dust, compressing them until they ignite to form stars. These stars then gather into vast galaxies, spinning wheels of light that dot the cosmic canvas. At even larger scales, gravity weaves galaxies into clusters and strings them along cosmic filaments, creating a vast cosmic web. It's a force so powerful, yet so subtly nuanced, that it enables the universe to be a place of complexity and beauty. It's a force so fundamental, yet so finely balanced, that even the smallest alteration could render the universe unrecognizable. Gravity, the fundamental force that structures the universe. From the Big Bang, the universe expanded. But how did it become so uniform? Let's delve into this cosmic conundrum. The answer lies in a concept known as cosmic inflation. This rapid expansion of the universe occurred in a fraction of a second after the Big Bang. Cosmic inflation is not just about size, it's about smoothness too. Picture a crumpled piece of paper. If you blow it up to the size of a football field, those crinkles and wrinkles seem almost flat, almost smooth. That's what cosmic inflation did to the universe. Now, why does this matter? Well, this inflation theory helps explain the uniformity we observe in the universe. Without this rapid expansion, different regions of the universe wouldn't have had time to interact, to share information, to balance out. It's this inflation that smoothed out the cosmic wrinkles, leading to a uniform universe. So, when we gaze at the night sky, we're seeing a testament to the power of cosmic inflation, a phenomenon that shaped the universe as we know it. Inflation smoothed out the cosmic wrinkles, leading to a uniform universe. Dark matter and dark energy, the invisible architects of the universe. As enigmatic as they are influential, these two cosmic constituents play an integral role in the cosmos's structure and evolution. Dark matter, although unseen, exerts its presence through gravitational effects, helping galaxies maintain their shape and preventing them from tearing apart. On the other hand, dark energy, the mysterious force accelerating the universe's expansion, affects the large-scale structure of our universe. It's like an unseen conductor, guiding the cosmic symphony. Imagine a universe without dark energy. It would likely collapse under its own weight. Conversely, too much dark energy could push matter apart, preventing galaxy formation. It's a delicate balance, and our universe seems to have hit the sweet spot. These unseen entities are pivotal in the universe's grand design. Their presence, though invisible, is felt in every corner of our cosmos, shaping the universe as we know it. In the microscopic world of quantum mechanics, perfection takes a different form. Here we uncover an intricate dance of particles and forces, a ballet of creation and annihilation. Quantum mechanics, with its inherent uncertainty, may seem at odds with the notion of a perfect universe. Yet it is this very uncertainty that allows for the richness and diversity of the physical world. Consider the principle of superposition, where particles can exist in multiple states simultaneously until observed. This principle is key to the functioning of everything from the humblest molecule to the most advanced quantum computer. Or take quantum entanglement, a phenomenon so strange that Einstein himself called it spooky action at a distance. Yet, without entanglement, we wouldn't have the complex chemical reactions that underpin life itself. So, while the quantum realm may seem strange and counterintuitive, it's a crucial part of the cosmic symphony. Even at the quantum level, the universe seems to be finely tuned for life. Could our perfect universe be just one of many in a vast multiverse? This question introduces us to the multiverse hypothesis, an intriguing concept that has sparked numerous debates among scientists and philosophers alike. This hypothesis proposes the existence of potentially infinite universes, each with its own set of physical laws and constants. Now think about this. If there are countless universes out there, different combinations of physical laws and constants are likely to occur. In such a scenario, our universe, with its perfect conditions for life, might not be so rare after all. It would be just one of many universes where the right conditions coincidentally lined up. So, the multiverse hypothesis provides a sort of cosmic lottery explanation for the so-called perfection of our universe. It's like hitting the jackpot, but in a game with an infinite number of players. In a multiverse, our universe's perfection might not be so unique. The seemingly perfect universe has profound philosophical and theological implications. Let's delve into some of these considerations. Many philosophers have argued that the fine-tuning of the universe suggests purpose or design, an idea that resonates with theological perspectives. This view posits the existence of an intelligent designer who fine-tuned the universe's constants to allow life. On the other hand, some philosophers propose a naturalistic interpretation, stating that our universe is just one among countless others, each with different physical constants. In this multiverse, it's not surprising that at least one universe would have the right conditions for life. Theological interpretations often vary as well, with some seeing the universe's order as evidence of divine action, while others argue that a perfect God would create a universe capable of developing and evolving on its own. Understanding the universe's perfection can lead to profound insights about our existence. However, the concept of a perfect universe is not without its critics. Some question the validity of the anthropic principle and the fine-tuning argument, suggesting alternative explanations. One such critique is the multiverse hypothesis, suggesting an infinite number of universes with varying physical constants, making our perfect universe just a statistical inevitability. Another critique is the assertion that our understanding of physical laws and constants is still evolving. What we perceive as fine-tuned could be the result of incomplete knowledge. For example, the values of dark energy and dark matter, which play key roles in our universe's structure and expansion, are still areas of active research. Additionally, some propose that life could exist in a universe with different physical constants, challenging the idea that our universe is uniquely suitable for life. These alternative explanations and ongoing scientific debates remind us that our understanding of the universe is continually evolving. The search for understanding continues, as does the debate on the universe's perfection. Our journey through the perfect universe is coming to an end. We've traveled from the fine-tuning of physical constants through the anthropic principle to the cosmic constants that shape our universe. We've delved into the formation of stars and elements, the factors that create habitable planets, and the role gravity plays in shaping the vast cosmos. We've discussed the intriguing concepts of cosmic inflation, dark matter and dark energy, and the microscopic perfection brought about by quantum mechanics. We've contemplated the emergence of life in this finely tuned setting, pondered on the multiverse hypothesis, and reflected on philosophical and theological considerations. We've also acknowledged critiques and alternative explanations that challenge the idea of a perfect universe. So, is the universe perfect? That's for you to decide. But one thing is certain, it's a fascinating place to explore.